this lesson, I want to introduce the very important concept of what's known as the electrostatic potential. I'm going to start kind of by bridging this back to the idea of fields that we just got done with, though, and the forces that act on charged particles. So let me start off just by introducing you to a cat. And let's imagine this cat's just sitting there doing its cat stuff, minding its own business, and I come up and rub a balloon on this cat. And everybody knows that if you rub a balloon on a cat, the static electricity will transfer. There will be some charges that move from the balloon to the cat, and therefore I will wind up with a charged balloon, which I'll go ahead and get rid of, but leave behind a charged up cat. And I don't know this for a fact, but let's assume that the cat winds up with a positive charge on spread throughout its body, so that's why it's got that kind of glow to it. So I now have an electrostatically charged cat, and I'm going to take this cat and stick them in an electric field. And we'll make it a uniform electric field, so maybe between two parallel plates or something like that. And if I do that, then what's going to happen is I have a charged object in an electric field, so there'll be a force on it. There'll be a force that acts on that cat in the direction the field goes, and the force is equal to the charge times the field strength. And that gives us a mass times acceleration, and we can play all sorts of games with calculating the motion from the acceleration if we want to. It's not terribly difficult to do if I have a uniform field, but it will get more difficult if I have a non-uniform field, so there might be a better way of handling this. But to get there, I want to go back to looking at that cat one more time. And think about that cat, and if I were to move him a certain distance, let's just take him and nudge him up by a distance delta r, and this is moving an object in the presence of a force, so therefore work is being done. The force is Q times the field, so it's Q sub cat times the electric field strength. And the work will be the force dotted with the distance. This is back from Physics 140 information, just the definition of work, what work is. If you don't like vectors, we can write that as F delta R times the cosine of theta, where theta is the angle. And in this case, I've actually drawn that angle to be 0 degrees, so the cosine is going to go away. So the work done on this particular cat is the charge on the cat times the electric field strength times the distance that I have moved and the displacement he's gone through in that vertical direction. Now, I'm going to point out to you, and I'm not going to really prove it by much, but I'm going to say, what if we took this cat and instead let him scamper around a little bit until he wound up going through the same displacement, net displacement at the end. So he took a different path to get there, but did the same thing. Now, I'm not going to mathematically prove it, but you can kind of imagine that if I broke that path that cat went on up into little tiny segments, the only thing that really matters is when he's moving upward. The side to side doesn't do any work, so it's only the upward part of the motion that matters. So therefore, this work actually is path independent. I could have taken any path I wanted to, so long as I wind up back at the same spot, then I have the same amount of work being done. And in fact, if I close the path and bring the cat back to where he started, the total work winds up being 0. If work is path independent, then we can take this force and refer to it as a conservative force, and conservative forces lead to conservation laws and potentials. So I have a potential energy, delta U, which is the negative of the work done. Now the way to think about this is when I let that cat go and move, he's moving in the direction the field goes, so therefore he's gaining kinetic energy. There's positive work being done on him. A positive work being done, a gain in kinetic energy, means that he's losing potential energy that he had because he was in that spot where he was being pushed by the field. So therefore the potential energy being lost is the same as the kinetic energy being gained, the work being done by the field. So this particular work gives us a change of potential energy, which is negative Q of the cat times the electric field strength times delta R. Now I'm going to look at this for a second and define for myself something new here called the potential difference. Not potential energy, but potential by itself. Delta U is the change in potential energy, but I'll notice here that the E delta R would be the same if that was a charged up cat versus a charged up pigeon versus a charged up buffalo. It doesn't matter what I put in that spot. The E delta R is the same. So let's take that E delta R and define it as being something new, and I'm going to call it delta V, where delta V is the change in potential energy that a charged object would experience going through that change in delta V. So delta V is delta U divided by, in this case, Q cat, and that's equal to negative E times delta R cosine theta. And I'll just look at the units on this. Delta U is in joules and Q is in coulombs, so a joule per coulomb is something we're going to define to be a volt. And this is how you actually know potential more commonly is a lot of people, instead of calling it a potential difference or a change in potential, they'll call it voltage. The electrostatic potential is the potential energy a charge of 1 coulomb would have if placed at a particular position, and the change in potential is the change in potential energy it would have if moved through a particular distance. So for instance, if I drop by 10 volts and I have 1 coulomb and I take it through that change of 10 volts, it's going to change its potential energy by 10 joules. Changes in potential may be related to the changes in potential energy simply by multiplying the size and the sign of the charge. So the potential energy is exactly the same as you'd play with in conservation of energy equations, that the final total energy is equal to the initial total energy plus the work of non-conservative forces. Or another way of saying it frequently is that the work of non-conservative forces is the change in kinetic plus the change in potential. But in this case, the change in potential energy is Q times that delta V. And I want to point out here that the sign matters on that Q. If I have a positive charge and I take it through a change in position where the voltage increases, then its potential energy is going to get bigger. That if I go from, say, 0 volts to 100 volts with a charge of 1 coulomb, I've gained 100 joules. But if that charge is negative, it's losing potential energy by going that way. So therefore, positive charges are going to want to go in directions that take them to lower potentials, because that will decrease their potential energy and increase their kinetic energy. Negative charges are want to go to places with higher potentials, higher voltages, because that will decrease their potential energy and increase their kinetic energy.